Hi all, can everybody hear me?
Yep.
Okay, great. I apologize. I'm not sure what's going on with my video. I've been rebooting to try and get it to work, but for some reason, I'm guessing you cannot see me, right? My
Nope.
camera is not working with Zoom right
Yeah,
now.
it's a blank screen and a
Okay,
black screen.
okay, that's fine. But I'm here, and I guess the main thing is that you'll be able to see the whiteboard, and I'll try and fix this for next time. Let's now share screen on the iPad. Okay. Um, I did. Hopefully, you guys saw the announcement from Piazza. I was able to expand the size of the course. So I think everyone who wanted to be in the course to enroll can. And I've sent enrollment codes to everyone who I think wanted to be in the course. If I missed you, please let me know. Um, I know some of you have tried to use the enrollment code and got put on the wait list instead of getting put in the course. That will be fixed. I don't know what's causing that, but I'm talking to people in the department to make sure that you're actually enrolled. Okay. And we do have a new GSI. That's Fred Jong, and his information is on the website under staff, so you can check him out there, and he'll see all the staff emails as well. Okay, so let's get started. Today, I want to introduce a technique, and I'll apply it to distinct elements called geometric sampling. And it's a case study, again, distinct elements. But this is a technique that gets used for a lot of problems. And I also want to talk about lower bounds. How do you prove that there is no streaming algorithm or there is no sketching algorithm that uses less than some amount of memory? Okay. So let's start with geometric sampling. Right, so we have a stream of updates coming, let's say, from some universe 1 to n. And the main idea in geometric sampling is to pick some hash function mapping that universe into, say, a range of size log n, where kind of the probability that h of I equals j is roughly 1 over 2 to the j. Okay, so for example, one way to do this is, pick another hash function h tilde that maps the universe into itself, and pretend that n is a power of 2. And then what you say is that h of I is just the index of the least significant bit of h tilde of I, right? So for example, if h tilde of some input is in binary this, then this is bit number 0, bit number 1, bit number 2, and 3. So the least significant bit is this one. So we would say h of I is 3. Okay. And the probability of that happening in this is 1 over 2 to the 4, because you need to have those 3 zeros, and then that has to be a 1. What's the probability that happens? It's 1 over 2 to the 4. So it's roughly 1 over 2 to the j, up to some factor of 2. Okay. And why am I doing this? So the idea is, we have some data structure that maybe solves some simpler version of the problem. So I'm going to show you an example for that with distinct elements. And maybe the simpler version in the case of distinct elements is we have a data structure that can solve the problem when the number of distinct elements is small. And I guess that's obvious, right? If I tell you that the number of distinct elements is at most 5, well, you can get away with at most 5 words of memory, where a word is log n bits. Just remember all distinct elements you've seen in the stream, right? If there are only 5 of them, you're only going to need to remember these 5 names. Okay. So the idea is like you have a data structure that can solve some special case of the problem, like for example this, where you have a bound on the number of distinct elements. And what you're going to do is you're going to basically create, let's say, partition the stream into log kind of substreams. And let's call these S1 up to S log n. Actually, let me start it with S0. S0 up to S log n, where kind of Sj is the stream restricted to the updates where h of I is equal to j. Okay. And then you're gonna feed each Sj into a separate data structure dj. So each level of this sampling has an associated data structure which processes just that substream. And then at query time, you're somehow going to figure out what to do. Okay. Maybe your answer is going to come from just one choice of j, one choice of Sj. You're going to query the corresponding dj and somehow modify your answer to get an answer for the entire stream. And there's some art there in how do you choose which dj to use, and how do you adjust the answer for dj to get an answer for the entire stream. That's that can be problem specific, but there are a lot of problems where you use this kind of general architecture. So let's be a little more specific now for how would you use such a thing for distinct elements. So more specifically, for distinct elements. Here I have, a special case of the problem where we're promised that the number of distinct elements T, this is the number of distinct elements, and I've been calling it T, but let me call it, for historical reasons, it's also often called F0 of the stream. And when we talk later about norm estimation in data streams, I'll explain where this term came from, why it's called F0. But we're promised that the number of distinct elements is at most k. And now, given that promise, we want to compute the number of distinct elements exactly. And kind of trivially, you can do this in k times log n bits of memory, right? Which is exactly what I said. You just remember all the distinct elements that you saw, right? If you see something that's not already stored in memory, you add it to what you're storing. And I should also mention that, if the promise is violated, we can detect it in this case, right? If you promise me that the number of distinct elements is at most k, but then when I process the stream, you actually give me a stream that has more than k distinct elements, I'll notice that, right? Because at some point I'll see the k plus first element and I'll say, wait, this doesn't match anything that I'm currently storing. And I can throw an error, right? So there is a data structure that solves the special case of the problem. And the memory, just trivially, is at most k log n bits. So we're going to use this data structure as our data structure to solve this special case. And we're going to use it.
N in this case?
N is the size of the universe. So you're imagining that all stream updates you see are integers that come from 1 to n. So for example, right, you're seeing a traffic stream, network traffic, you're seeing packets, and I want to know how many distinct IP addresses sent traffic on this link today. So then N is like how many IP addresses exist in the world, and the answer is 2 to the 32, or maybe 2 to the 64 if it's IPv6. But it's just the size of the universe that the items are coming from. That's what N means.
Wait, why do you need klog?
You just remember you just remember all the elements that you're you just remember all the elements that you're seeing in the stream, right?
Wouldn't you only need login for that?
But there are k of them, right? So writing down the name of one element takes log n bits.
Oh, I see. Oh,
But
yeah. Okay. I
but
see.
if there are k at most k distinct elements, you might need to spend k log n bits to remember the
Right.
k.
Right. Okay. Yeah. Yeah. Right.
Yeah.
Oh,
Okay, great. So so the algorithm is going to be something as follows. There's going to be the rough idea. We're going to have to make some adjustments. It's going to have to get a little bit more complicated, but not too much more. So we're going to pick k to be some constant to be determined over epsilon squared. Remember, we want to know the answer up to a 1 plus epsilon factor. So we're going to set k to be this. We're going to initialize d prime to be, the trivial data structure, like this one. Okay. And then we're also going to initialize d0 up to d log n to also be other copies of the trivial data structure. And we're also going to pick a hash function mapping the universe into the range log n. Let's call it, be a little more specific. Such that, probability that h of I equals j is, this roughly 1 over 2. Let's just say it's 1 over 2 to the j from pairwise independent family, right? To be more specific, remember I said that, h tilde maps from n to n. I mean, the way I defined pairwise independence, I said, that you want that the probability that things map to somewhere is uniform, right? And if you look at two things at a time, the probability that those two things map to some two things in the range acts as if it were a uniformly random function. But here it's not uniformly random. It's this geometrically decreasing probability, right? The probability that h of I equals j is 1 over 2 to the j. But what I really mean here is, as I said, kind of h is just the least significant bit of h tilde. And h tilde is a uniform random hash function. So h tilde should be drawn from a two-wise independent family, right? Where h tilde is this thing that I said here. Okay. So h tilde, it looks like it's uniform. If you look at two things at a time, it's drawn from a two-wise independent family. So if you look at two indices, I and I prime, well, the probability that h of I is equal to j and h of I prime is equal to j prime is going to be as if they were independent. So it's going to be like 1 over 2 to the j times 1 over 2 to the j prime. Okay. And now, instead of writing pseudocode, let me just draw the picture. So you see update I in the stream. Okay. What do you do with that? Well, you have this d prime here. So d prime is going to get that update. And then you also have the other, d0, d1 up to d log n. So, and what you also do is you also send this into h of I. H of I is going to give you kind of a random one of these data structures. It's going to be biased toward d0, right? Half the time I get sent to z. Half the indices get sent to d0. A quarter of the indices get sent to d1. An eighth gets sent to d2, etc. Most of the time it goes to a lower d. So it's going to send you to a random one, but with this geometric bias. And that's how you process an update. Hopefully that picture makes sense. So you send all updates to d prime, and you also send an update to a random data structure based on the hashing. Okay, so each update gets sent to two different Ds. Okay, so that's how you do an update. How do you do a query? Okay. So the first thing you do is you check D prime, right? If the total number of distinct elements is less than k is what I told you. We set k to be a parameter, right? K is this number, c over epsilon squared, where c we're going to determine c later. So if the number of distinct elements is at most k, then D prime will tell you that, right? And it'll give you the right answer exactly. Okay. Otherwise, D prime will tell you no, the number of distinct elements is not less than or equal to k. It's more than that, right? In principle, it could be as big as n. And then what you're going to do is you're going to pick. So how do you do this? We don't know yet, but we'll figure this out. We're going to pick an R such that the number of distinct elements over 2 to the R is equal to theta of 1 over epsilon squared. Call this R star. And then what we're going to do is we're going to return 2 to the R star times dr star dot query. So of course this is bogus right now, because how do you don't know F0. F0 is the number of distinct elements, right? That's the thing we're trying to estimate. So if I say pick an R such that F0 over 2 to the R is something, I mean, I don't know F0, right? So how can I do that? We'll see that can be, there's a way to do that. Okay. But okay, so now what's the point? The point is, let's say that, let's try to understand what's happening here. So what do we know? We're picking such a thing. We're picking such an R such that F0 over 2 to the R star is less than or equal to, say, C2 over epsilon squared, and it's at least C1 over epsilon squared, where C2 is going to be something that's kind of much less than C. Remember what C is. C is the constant in the definition of K. Okay. So Chebyshev's inequality, right, is going to tell us that kind of the number of people who hash there, the number of distinct elements. So first of all, in expectation, how many distinct elements map to level 0? Half of the distinct elements map there. How many of them map to level R? A 1 over 2 to the R fraction map there, right? So in expectation, we're getting F0 over 2 to the R distinct elements that participate in the Rth substream. Okay. Now, the number that actually participate there is not going to be exactly F0 over 2 to the R. That's only the expectation. There's going to be some deviation from the expectation because this is a random process. What Chebyshev's inequality tells you is that, right, what do you expect your deviation to be? You expect it to be the expectation kind of plus or minus a constant factor times the standard deviation. I mean, by the way, right, I guess that's probably why, I don't know the etymology of it, but that's probably why the standard deviation is called the standard deviation, right? The standard deviation is defined to be the square root of the variance of a random variable. And kind of, it makes sense that it's called that because Chebyshev's inequality tells you that kind of the probability that a random variable deviates by more than a constant factor times its standard deviation is small, right? What's the probability that you deviate by more than 5 times your standard deviation? It's at most 1 over 5 squared, right? That's what Chebyshev's inequality tells you. So the number that we expect to see there is going to be F0 over 2 to the R star, kind of plus or minus the standard deviation, which is going to turn out to be kind of the square root of the expectation. So that's going to be something like plus or minus O of 1 over epsilon, which is the same thing as kind of 1 plus or minus O of epsilon times F0 over 2 to the R star. And so this is why we chose K the way we chose it. We wanted to make sure that the square root of the expectation was only an epsilon fraction of the expectation. So that's why we chose it, so that the expectation was 1 over epsilon squared. So that the square root was 1 over epsilon, which is an epsilon fraction of that. So good. So that means that if we can estimate, if we can find out the number of distinct elements at that level, with good probability, we're getting a value that's within roughly 1 plus epsilon of f0 over 2 to the r star. And then if we scale it back by 2 to the r star right here, we're getting a 1 plus epsilon approximation of f0. Okay. So this is all just kind of a high level discussion or kind of game plan for why we're doing what we're doing. But, maybe I'll do that Chebyshev's inequality a little more carefully and write out the math so you can see exactly why I'm saying this, that you're getting this from Chebyshev's inequality. And then the only other thing we have to do is to say, how do we pick this R? Because we don't know f0, right? So that's the game plan, is to address those two things. Before I start on that, any questions about the strategy?
What's D prime doing?
Yes. So I should have written it down, but the first thing we do during query is actually, the first thing we do, I'll put it right here, is we first check D prime. Okay. So the first thing we do is we check D prime. We ask it, is the number of distinct elements at most K? It knows that because remember this special case, we have this trivial solution can answer that for us. So we ask it, is the number of distinct elements at most K? If so, D prime will tell us the answer exactly. Otherwise, if it's bigger than K, then we do this other stuff. So that's what D prime is for. And so why is that necessary? The reason it's necessary is, if the number of distinct elements is small, then there is no such R, right? Like D0 is half the distinct elements, D1 is a quarter of the distinct elements, etc. Well, if the number of distinct elements is at most 10 to begin with, then there is no level that receives 1 over epsilon squared distinct elements, because there aren't 1 over epsilon squared distinct elements. There are only 10 in the entire stream. Does that make sense?
So is D prime guaranteeing that we have like the good probability bounds, where it's like the exact solution on like the small number of like where we see a small number of elements?
Yeah. So the problem is, like, we want to estimate f0 based on some dr where f0 over 2 to the r, some dr star, right, where f0 over 2 to the r star is up to a constant 1 over epsilon squared, right? That's what we'd like to do. The problem is there might not be such an r, right? Because if the number of distinct elements is t, then at level 0, t over 2 land there, kind of an expectation. And at level 1, t over 4 land there, etc. And at level 2, t over 8, etc. But if t is less than 1 over epsilon squared to begin with, none of these numbers is going to be theta of 1 over epsilon squared. And that's where D prime comes in. D prime is there to help us is there to answer our queries when there is no such R. Right? So for example, let's say, for the sake of setting constants, let's say that I want, specifically what I want is f0 over 2 to the r to be at most, 10 over epsilon squared and at least, 1 over epsilon squared. I want an r such that this holds. But if the initial, so let's say f0 was, you know, 1,000 over epsilon squared, how can I choose r? I just need to choose r such that 2 to the r is roughly 100. So, you know, I can choose r to be like 7, right? Then 1,000 over epsilon squared divided by 2 to the r is in this range. But, you know, if the initial f0 is 1 over epsilon, then there is no such r, right? Because the original f0 is already too small. So there, I can't hash it. I can't hash it to make it even to make it bigger. Hashing it will only make it smaller. In this case, we'll use d prime. Okay, so does this answer the question?
Yes, to me. Someone else asked a similar question, so I don't know if it answers it for them.
Oh, but it answers your question.
Yeah, and then also one thing, just like kind of help build intuition. Can you explain like kind of like what happens on a query? Like, what's the actual like number that we get? Like, and where does that come from after we've had more than k elements?
Yeah. So, for example, let's say in this case, I said we choose r is 7, right? So right there,
Yep.
so there is some data structure d7, which received all the streaming updates such that the index of the least significant bit was the 7th bit, right? And that d7 data structure is the trivial data structure, which just remembers the first k elements it saw, where k is this c over epsilon squared. Okay.
Mhm.
So what does our query return? It asks d7, how many distinct elements did you see? It gets a number, and then it scales that number up by 2 to the 7. And that's what we return.
Gotcha. Perfect.
Okay. Okay. So the question, how to identify an R such that f0 over 2 to the R is theta of 1 over epsilon squared. And kind of the key insight here is to notice that to be able to do this, you don't need to know f0 exactly. You just need to know it up to a constant factor, right? And then whatever, you know, that number you have, which is a constant factor approximation, you just use that as your substitute for f0, and then you calculate an R based on that, right? So basically, you know, you would like to set R to be something like the logarithm of epsilon squared f0, right? That's what you'd like to do. It has to be an integer, so let's say this. But, you know, you don't actually know f0. Let's say you only know it up to a constant factor. So that estimate is f0 tilde, which is your constant factor estimate. So you'll set R to be this. So the question is now, of course, how do you get this? How do you get a constant factor approximation to f0? So what you've seen so far is if we had a constant factor approximation to f0, then there's a way to refine it into a 1 plus epsilon approximation via everything you've seen so far. You know, you have this d prime, you have these other log n d's, you have this hash function with geometric sampling, and then you just basically plug into that and you get what you want. So how do you get this f0 tilde? So let's say getting a constant factor approximation to f0. How do you do that? So what we're gonna do the same thing, but we don't need the d prime anymore. Without d prime, and with k just being 1. So we're gonna have d0, we're gonna have d1, we're gonna have d log n, and each one of these, this is some dr. This is each one of these. Just remember the first element ever seen. So, I mean, this is a really stupid data structure, right? This is, if the number of distinct elements is at most 1, then I can tell you how many distinct elements there have been. Otherwise, as soon as the number of distinct elements is more than 1, so it's at least 2, then this D doesn't know anymore. It's the same trivial data structure, but instead of instantiating it with K being 1 over epsilon squared or C over epsilon squared, we're now instantiating it with K being 1. Okay. And so kind of let's say that the number of distinct elements is actually root n. Now let's give an example. Kind of tell me, what do you expect this picture to look like? How many distinct elements do you think d log n has seen? What's a typical number that, in a typical run of the algorithm, how many distinct elements has d log n seen if the number of actual distinct elements is root n?
Would it be 0?
Yeah, 0, right? Because in expectation, you see, the expected number that land there, right? Just remember, you can define these indicator random variables, right? Like yij is equal to 1 if, let's say, h of I is equal to j and 0 otherwise. So the expected number of distinct elements kind of at level j is the expectation of the sum I goes from 1 to n of yij, which is the sum of the expectation of yij, right? And what's the expectation of yij? It's just the probability that yij equals 1. And of course, this is 1 over 2 to the j, right? And actually, this is not I equals 1 to n. This is basically I equals, I should really say this is more like I equals 1 to f0. Or let's actually say it like this. Let's call this t. No, I'm using t already for something else. Let's call this q. So this is like I sub q, and I sub q. So this is like the qth distinct element, right? Not all n elements are actually not all n universe elements appear in the stream. Only f0 of them do, right? So this is equal to f0 over 2 to the j, right? So the expected number of distinct elements that appear at level j is f0 over 2 to the j. So the expected number that appear in d log n is root n, f0 is root n, divided by 2 to the log n, which is n. So it's root n over n, which is 1 over root n. So the number that appear is, f0 over 2 over n in expectation. So what's the probability that you see at least 1? Implies the probability that you see at least 1 element there is at most n over f0 by Markov's inequality. Right. The probability that a random variable is, is lambda times its expectation is at most 1 over lambda. So here, this expectation is root n over n, 1 over root n. So the probability that you see 1 element, well, 1 is root n times the expectation. So the probability that you see 1 element is at most 1 over root n. So it's very unlikely. It's very unlikely you'll see anything there. And the same is true as you kind of go up. As you go up, as long as the expectation is much, much less than 1, it's very unlikely that you'll see anything. Until what? Until you get to an R such that the expectation is not very small. The expectation is like at least a constant. Let's say, if the expectation is at least a quarter, so you're just, so f0 over 2 to the r is 1/4, then the probability that you see an element there is, all you can say is that it's at most a fourth, which is a decent number. It's not too small. Like there's a decent chance you see something there.
So Jelani, is that the case? Because if f0 increases, the probability of seeing more than one element decreases. right?
Yeah. So okay. So actually, so here, yeah. Okay. So I'm just looking at the probability that you see at least one element. You might see two. Does that answer your question?
Right. But I mean, as written, is it still not the case if f0 gets larger, the
Yeah.
probability you see greater than one element becomes smaller?
No. If f0 is larger, then the probability you see greater than or equal to one element also becomes. Oh, I see what you mean. No. Yeah. So
Right.
yeah. So actually, I inverted it. I think that's what you're saying. This should have actually been f0 over n.
Okay.
Right. So let's be a little more careful. So what's the expectation? The expectation is
That
as
makes sense,
f0
yeah.
over n, right? The expectation is f0 over n.
Yeah,
So
yeah.
the number one is n over f0 times the expectation. So it's like lambda times the expectation, where lambda is n over f0. And Markov says the probability of this happening is at most 1 over lambda.
Got it. No, that makes sense. So
so-
it is inverted. Yeah.
Yeah, so this is, I should have said f0 over n. Okay? Or in general, it's going to be like f0 over 2 to the r at level r. Right? So as soon as you get to an r such that, f0 and 2 to the r are comparable up to a constant factor, then there's a decent chance you see it. You see an element. So, okay, so what this says is so let's say that there's some actual like optimal r stars. So let's go back to, let me draw more. So let's say that this is d sub log of f0, log base 2 of f0. And let's take the ceiling or something. And then, there's some others here, there's some others here, there's some others around it. Okay, let's do one more. So, right, the probability, the probability that this level, like, has any elements is at most 1/8, right? And the probability that, because it's 3 levels below the logarithm. So f0 over 2 to the r here is basically an 1/8. And then the probability that this one right here has any elements is at most a 16th, etc. And you get this kind of geometric decay. So the probability, let's define this now, red region. The probability that the red region has any elements at all is at most an 1/8 plus a 16th plus a 32nd, etc., which is at most a quarter. And of course, I could have slid this down just by 1. I could have defined the red region to be just kind of 1 level lower, and then I would have gotten an 1/8. Right? Okay? So it's very unlikely by union bound that I see anything at all in this red region. At the same time, if I go just a couple levels higher, so let's go like 4 levels higher. So 1, 2, 3, 4 levels higher. And I expect there's this very small issue here because of rounding, right? The log base 2 of f0 might not be an integer, which is why I put the ceiling there. If there had been no ceiling and this had been an integer, if I go 4 levels higher, I would expect to see 16 elements there. Because of the rounding, maybe all I can say is I know I expect to see at least 8 elements there, maybe. Or strictly more than 8. Okay. So kind of what's the probability that I see 0? So that means it's unlikely that I see 0 elements, right? Because again, the standard deviation is like the square root of 8. So I typically see kind of 8 plus or minus the standard deviation, which is like, root 8. So the probability that I see less than, 8 minus c root 8 elements is kind of at most 1 over c squared by Chebyshev. Right, so it's unlikely that I'll see 0. Okay, because I have to deviate a lot from my expectation to see 0. So, so in summary, to get a constant factor approximation of 0 tilde to f0, just return 2 to the r, where r is the largest integer, such that kind of dr dot query is not equal to 0. Does that make sense? And what this analysis says is, it's very unlikely that the output is in the red region. And it's also very unlikely that the output is above this level. So it's very unlikely, let me do this different color. It's very unlikely that the output is in this region as well. Which means that I kind of expect the output, the output's, with good probability, the output is going to be some r in this kind of teal region. And any output in that teal region is within a constant factor of the truth. This is basically the logarithm plus or minus 3 or 4 positions. Okay, does that make sense?
And so with this being in the teal region, does that get us our like epsilon approximation?
No, that'll give us a constant factor approximation.
Okay.
Right? Let's say that the logarithm, let's say that f0 were actually a power of 2. So we don't have to deal with the ceiling on the logarithm. Then if the best case scenario is that the deepest level that has any elements at all is this level right here. None of the levels below it have anything, and this level has something. If that's the case, we're going to return 2 to the r for this r, and 2 to the log base 2 of f0 is exactly the right answer. Right? Remember, we're returning 2 to the r. But, we might get unlucky just kind of randomly, because this is a randomized process, right? And it might happen that the deepest element, the deepest level that has any elements, it might be one off. It might be this one, right? And if it's that one, then we're going to output an answer that's too big by a factor of 2, right? Because this r is 1 bigger. So 2 to the r, if the true r is r star, then 2 to the r star plus 1 is twice as big. Similarly, if we happen to output this one right here, that's 2 levels deeper, then we're going to output something that's 4 times bigger than what we're supposed to. And similarly, if we go higher, if we're unlucky and the log f0th level has nothing, maybe only this level has something, then we're going to kind of underestimate r by 1, and we're going to output something that's only half as big as we should. So we're going to underestimate by a factor of 2. Okay, but the point is, what we argued here is with like kind of decent constant probability. If you do the number, this actually is already in the notes that I put on the course website. So if you want to see the calculations there precisely, after lecture, just take a look at the calculations. But the point is, with really good probability, I think what I wrote in the notes, the analysis I gave in the notes is with really good probability, you're gonna find the first time you're gonna see an element at a level is gonna be a level which was within a plus or minus 4 levels of the true level, which means that you're only going to be off by a factor of like 16 or something, 2 to the 4. Okay.
Awesome. Nice.
And that's enough to basically then do what we said here, right? Is to pick this, is basically to be able to pick an R such that this is true. Right? That's why we wanted to do this, and we're going to be able to do it. And that's it. Okay. So, I do want to talk about some other stuff before the end of lecture. So I don't want to go through kind of all the calculations in detail, but there is one calculation that maybe is not super obvious if you haven't, you're seeing this for the first time, which is, this assertion I made that you're typically going to see kind of 8 plus or minus root 8. Why am I saying that? So let me just kind of write that down so you can see where this is coming from. So I said that kind of yij, or let's say yiqj, is equal to 1 if the qth distinct element maps to level j. Basically, in other words, kind of h of iq is equal to j, and 0 otherwise. So we know that the expectation of yiq j is equal to 1 over 2 to the j. And we know if we define y to be the sum, q goes from 1 to f0 of yiq j, we know that the expectation of y is equal to f0 over 2 to the j. Now, what about the variance? Okay. The variance of y is the variance of the sum yiq j, I goes from 1 to f0. And this is equal to the sum of the variances and this only holds, this equality holds because we drew the hash function from a pairwise independent family. Right? Linearity of expectation always holds. It doesn't, it doesn't require independence of the underlying random variables. Like the expectation of the sum is always the sum of the expectations. That is not true for variance. The variance of the sum is not always equal to the sum of the variances, but it is true when you have two-wise independent random variables. And why is that? Just recall kind of the variance of y is equal to the expectation of y squared minus the expectation of y squared. By linearity of expectation, this does not require independence to calculate. What about this? You can expand it. This is the expectation of the sum of yiq comma j squared, which is equal to the expectation of the sum over all q and q prime of yiq comma j, yiq prime comma j. Right? Linearity of expectation says I can pull this inside so I can get the expectation here. Okay. And let me break this up into kind of this. There's the two cases. There's a case where q equals q prime and where q is not equal to q prime. So this is the sum over q of the expectation of yiqj squared, but y is a 0, 1 random variable. 1 squared is 1, 0 squared is 0. So squaring this random variable doesn't do anything, so I don't have to square it. Plus the sum of q not equal to q prime of the expectation of yiq comma j, yiq prime comma j. Now, if the hash function were totally random, right? What does this random variable mean? What does the product mean? It means that the qth element and the q primeth element both got hashed to level j. Both of them got hashed to level j. Okay. So what would the probability of that be if this hash function were totally random? it would be 1 over 2 to the j times 1 over 2 to the j. It'd be the square of 1 over 2 to the j, right? Normally, this would be the expectation of the product would be the product of the expectations. This would be the expectation of yiq comma j times the expectation of yiq prime comma j.
Professor, is the in the sum beforehand, are those values squared?
Do you mean when you say the sum beforehand? Do you mean
The sum
the sum?
before the sum below that, but not the one where you're comparing q and q prime.
You mean do I have a square? Do you have a squared here?
Right. Yeah. Right there.
Yeah. So that was what I was saying. I mean, so you can put a square there if you want to, but it doesn't matter because
Oh, they're indicators, right?
they're 0, 1 random variables. So it's the
Sorry,
same.
sorry.
It's this. Yeah, no problem. It's the same even if you don't put the squares. So the point is, like, I would like to do what I did right here. I would like to say that the expectation of the product is the product of the expectations. That's only true if these two random variables are independent of each other, right? But that's exactly what pairwise independence says, two-wise independence. It says if you look at two random variables at a time, those two look like they're independent, okay? So that allows me to change the expectation of the product into the product of the expectations, which is why what I said above is true, namely this thing right here, right? The variance of the sum is the sum of the variances whenever you have pairwise independent random variables. Okay. Okay. So anyway, that's why we were able to get away with a two-wise independent hash function. Now that you have a two-wise independent hash function, of course, what is this? What is the variance of yiqj? Well, this is a 0, 1 random variable. It's a Bernoulli random variable, right? Meaning there's some probability it's 1. There's some probability p it's 1. There's some probability 1 minus p that it's 0. What's the problem? In general, whenever you have a Bernoulli random variable, the variance is p times 1 minus p, right? It's the expectation of the square minus, right? It's exactly this. It's the expectation of that random variable squared minus the expectation of that random variable squared. So this is, again, a 0, 1 random variable. Squaring it doesn't do anything, so you can ignore this square. So this is p minus p squared, which is equal to p times 1 minus p, which is always at most p, right? Which means that this thing is at most p times f0. And what's p? P is 1 over 2 to the j. So this is f0 over 2 to the j. So just as I said, the variance is at most, in fact, less than the expectation. Okay.
Wait, what's j when we're considering the full y?
J is the level that you're hashing to. If you want, I can call it. If you want, I can call this thing yj. Yj is just how many distinct. Y here is how many distinct elements hash to level j.
Oh, okay.
And in expectation, it's f0 over 2 to the j. The variance is also at most f0 over 2 to the j. And then now we can do Chebyshev. What's the probability that, let's say, the number of distinct elements at level j minus f0 over 2 to the j, what's the probability that I deviate by more than c times the square root of f0 over 2 to the j? By Chebyshev, this is at most the variance of the number at level j divided by c squared times f0 over 2 to the j. Basically the square of the right-hand side. But we just said that the variance is at most f0 over 2 to the j. So this is at most 1 over c squared. So that's what I'm saying, kind of typically what you see typically kind of level J will have f0 over 2 to the j plus or minus kind of O of square root of f0 over 2 to the j elements. Right, so that's why I said if you expect 8 elements, you typically expect a deviation of, on the order of square root of 8. So, if you, that means that if you have 0, if you expect 8 and you see 0 elements, you deviated by square root 8 times square root 8 from your expectation. And the probability of that happening is at most 1 over square root 8 squared. So C is basically square root 8. So it's at most, the probability of that happening is at most an eighth. So it's unlikely that you see 0 elements when you expected 8. It's even more unlikely that you see 0 elements when you expected 16. Right? That would happen with probably at most 1 over 16 by the same argument. So does that all make sense? Any questions?
Can I ask something back about like in the original algorithm with like using R?
The original, yeah. So okay. So first of all, kind of just so we're all on the same page, we're basically running 2 algorithms in parallel. One of the algorithms is there to get you a constant factor approximation, okay? And that algorithm is basically this picture, right? That algorithm is you maintain these log n different data structures, each with k being 1. And in parallel, you also maintain kind of this data structure, which looks awfully the same. It's just that it has a higher k, right? Instead of k being 1, k is c over epsilon squared. And you also have this d prime on the side, which is just kind of to handle the special case, the corner case, where the number of distinct elements is small to begin with. Okay. So now the overall algorithm, what is the overall algorithm doing? Whenever you see I in the stream, you send it to the other data structure that gets you the constant factor approximation. You feed it there. You also feed it here in this red box, which itself feeds it to 2 places. It feeds it to D prime, and it feeds it to D of HI. And then when you want to answer a query, what do? The first thing you do to answer a query is you check D prime. That's going to give you the right answer if the number of distinct elements is small. Otherwise, if the number of distinct elements is not small, okay, then you get a constant factor approximation from the other data structure that you're running in parallel. That's going to tell you kind of the right R to use up to an additive 3 or 4. Then let's call that R star. Then you're going to look back at this box. You're going to query dr star in this box. And then you're going to return that answer times 2 to the R star. So that's the overall algorithm. Does that answer your question, Noah?
Yeah, I think I wants to see how it works, but I was curious why don't we just pick the lowest R where the dr reports like less than k elements, and then use like 2 to the R times the query for that dr, because it seems like it would be more reliable for the lower drs when they have more elements.
Yeah, so you're saying, why do we go to the one where we expect 1 over epsilon squared elements? Why don't we go to the one where we see like 5 elements, or just some non-zero number of elements, right? Is that your question?
Yeah, like if there's a bunch of elements, d0 has like half the distinct elements. If that's way more than k, then you'll expect it to take a while to get to one that has less than k. But then why don't we just take the first one? It feels like that should be the most reliable.
So the answer basically goes back to this. Okay, so remember now, kind of at level R, we will typically see kind of f0 over 2 to the R, let's say plus or minus, some constant times square root of f0 over 2 to the R distinct elements. Right? which I will call, what do I want to call this? I'll call this, if I want to write this multiplicatively as multiplicative error instead of additive error, this is like 1 plus or minus O of square root 2 to the r over f0. This is an r. Times f0 over 2 to the r. So then when we scale this back up, by 2 to the r, what we're going to get is our final answer is going to be kind of 1 plus or minus O of square root 2 to the r over f0 times f0. So this right here is like our multiplicative error. In particular, this, we're getting basically this is alpha, and we're getting kind of a 1 plus or minus alpha approximation, right?
Wouldn't it be better to use the lower r, because then alpha would be lower? They should use the lowest r possible.
Oh, the lowest r, not the biggest r. Is that what you're saying?
Yeah, the lowest r.
Well, I mean, okay, so yeah, so I mean,
Well, the lowest r where dr doesn't report having too many, more than k elements that it gave up.
Oh, I see what you mean. Yeah. So that makes sense. Yes. You have to be a little bit careful in your analysis though, because like you're choosing, how should I put it? This is a randomized algorithm. What's the source of the randomness? The source of the randomness is H, right? Does it make sense? So if you choose the level, if you say like, the level I'm going to use is the highest level, basically the smallest r, so the highest level that doesn't say that I have more than k elements. So the fact that I'm picking that level is basically now it's like using up some of the randomness of H, right? The level I choose is correlated with the randomness of H. So now, conditioned on that level, if I want to understand something about the error I'm getting, I can't just apply Chebyshev's inequality because H is not totally random anymore, because I've conditioned on some event happening, and that event depends on H. Right?
Interesting. Yeah. Okay.
Does that make sense?
Yeah, like it was so
you have to be a little
harder to analyze.
So I'm being a little bit more careful about how I design my algorithm, just so that the analysis is not doing any funky stuff, right? I can't, and that's why, for example, I'm using two different data structures, one that gets the constant factor approximation and one that refines its 1 plus epsilon. You could say, why don't I just use the same data structure for both? Look at that first data structure that has a large K. Look at the largest R that reports a non-zero number of distinct elements. Use that as my constant factor approximation, and then choose the level to estimate based on that. But the problem again is, once I tell you which level has which is the deepest level that has a non-zero number of elements, that reveals something about H. And H, once I do that, H is conditioned on that event. H is not like random anymore. Or it's not like uniformly random anymore.
Yeah, okay. That kind of makes sense.
Yeah. So hopefully that answers your question. But going back to the question I thought you were asking, I guess this is why I chose R such that F0 over 2 to the R is roughly 1 over epsilon squared. Because I want this quantity, right? I want square root of 2 to the R over F0. This is an R, not an N. Sorry, my R's keep looking like N's. I want this to be roughly epsilon, which implies I should choose R such that F0 over 2 to the R is roughly 1 over epsilon squared. Okay. So in the remaining time, so that's it for the algorithm. Maybe I want to say maybe just a couple of remarks, and then in the last bit I want to say something about lower bounds. So the space here, H is from a 2-wise family, so it only takes log n bits to store. That's kind of small compared to everything else. There are log n levels times kind of k log n bits per level for each dj. So this implies, O of kind of 1 over epsilon squared log squared n bits of space. There are improvements that you can make on this basic idea. And this is, the ideas for this improvement are Bar Yosef, JRAM, Kumar, Shiva Kumar, and Trevisan in 02. The same people who introduced the KMV algorithm also showed that you can get something good out of this algorithm. So the first idea is this trivial data structure that remembers the first k elements it sees. It's using k log n bits. You can actually get away with k log k bits. So trivial data structure, you can do k log k bits instead of k log n bits. And why is that? The point is, if you're only keeping track of k elements, you can perfectly hash them into a range of size kind of O of, let's say, k squared, right? Again, this is this perfect hashing idea. If I have k elements and I hash into a range of size 100k squared, it's very unlikely that there are any hash collisions, okay? Which means that, I don't, nowhere in this algorithm do I actually care which elements I saw. I only care to count how many distinct elements I saw. So as long, I don't need to really remember their names. It's enough to remember random names as long as those random names are different. And if I give them random names in the range 1 to k squared, then by perfect hashing, it's unlikely that there will be any hash collisions. So I can basically, with decent probability, save on my memory for the trivial data structure.
Is it perfect or like a very, very low probability?
They shoot for perfect hashing. So, but it's not going to, it's not going to be a perfect hash always. It's going to be a perfect hash with high probability. I mean, our data structure overall is allowed to fail with some small probability anyway, right? So, if any of my perfect hashings fail, I'll just give up and I'll say, you know what, I failed. But, and actually I should be a little more careful. What they actually do is, if you want you can look at their paper for more details, but because there are log n levels of this, there are kind of k log n elements in total that, you want to say maybe all of them are perfectly hashed. So you'll map into a range of size k squared log squared n, which means that your memory will end up being something like k times log k plus log n. So you'll hash into a range of k squared log squared n. Okay. And the second thing that they do is rather than keep track of all these Ds, this is D0, D1, etc. There are log n of them. Rather than keep track of all of them, they kind of change their definition of H so that D0 will get all elements with the least significant bit of H of I being at least 0 as opposed to equals 0. And this will get all elements with the least significant bit of H of I being at least 1 instead of equal to 1, etc. Which means the set of elements that go into D1 is a subset of D0. The subset of elements that go into D2 is a subset of D1. And then what they do is they say, now we don't need to keep track of all these levels at the same time. Let's only keep track of D0. And then once D0 gets too full, we'll kick out all the elements that have a least significant bit of 0. And then we'll just rename the data structure D1. And once D1 gets too full, we'll kick out all the elements there that have a least significant bit of 1. And then we'll just call what's left over D2, which means we only need to keep track of one of these boxes at a time, not all log n of them. Okay?
And for the parallel data structure that gives a constant factor approximation, all we need to do is keep track, because since k is 1, all we need to keep track of is like, what's the largest least significant bit of any hash evaluation we've ever seen. That will tell us what the deepest level is that got hit, right? So we don't even need to remember the name of any element at all. We just need to keep track of that index of what's the deepest least significant bit. And in fact, that's what's, as Professor Hellestein mentioned to me in kind of a recent meeting, that's what's usually described as the Flageolet-Martin algorithm, by the way. Just keeping track of the largest distinct element you've ever seen to get a constant factor approximation. So kind of overall, what we said is you can basically kind of get rid of this log n for the number of levels, and you can also replace this log n by log k plus log n. You also need log n bits to store the hash function. So the final space after you make these optimizations is going to be something like 1 over epsilon squared times log 1 over epsilon plus log n plus another additive log n just to store the hash function. And this is actually almost optimal. This part is suboptimal. And as I mentioned, there's been work. I had a paper with Daniel Kane and David Woodruff in 2010 that showed that there's another data structure that doesn't have this extra log 1 over epsilon plus log n factor. Okay. So that's it. Questions about any of this?
This is just for constant failure probability, right?
Yes. And then if you wanted failure probability delta, you could do the usual trick of running log 1 over delta of these in parallel and outputting the median result. That would give you the whole thing here times log n, times log 1 over delta. But the true optimal bound is O of 1 over epsilon squared log 1 over delta plus log n. And this bound is due to Yaroslav Błaszczyk. Not too long ago, 2018. It was in SOTA 2018. So here, it's interesting. The log 1 over delta doesn't have to multiply the log n. So he's doing something a little bit more clever than simply, getting constant failure probability and then repeating it log 1 over delta times, because if he did that, then the log 1 over delta would multiply the log n as well, which it doesn't have to. Okay. Any other questions?
Go ahead.
Go ahead.
I was wondering about sorry? Maybe I'm interested. Someone else want to go?
Three of us all talk to at once.
Someone else go first.
Okay, I was just going to ask where the big C came from earlier.
Oh, where does the big C come from in K? So if you want to see the details of how to choose big C appropriately, that's in the in all the detail. It's written in the lecture notes right now. You can already find it on the website. But basically, the idea is, we only can know based on that parallel data structure. We'll only know F0 up to a factor of like 16, right? So we might overshoot, and we might choose a level such that the expected number that maps there is 16 over epsilon squared, right? And then because of Chebyshev's inequality, there's it's kind of standard to have a deviation of roughly 4 over epsilon, which is square root of 16 over epsilon squared, right? In fact, it's kind of standard to have a deviation of, let's say 4 times the standard deviation. So it's kind of common to have a deviation of 16 over epsilon, right? Which means that kind of at the end of the day, what you'd like to do is set K to be something like maybe, let's say 32 over epsilon squared. Because it's very unlikely that even at the level that you base your estimate on, it's very unlikely that the actual number of distinct elements there is bigger than 32 over epsilon squared. Does that make sense?
Yeah.
Okay. Any other questions?
Well,
So-
I was wondering about kind of implementation of this and similar algorithms. Like I was
Yeah.
like looking through the lecture notes and I noticed like you said like commonly like use hyperlog in practice. I
Yeah.
was wondering like maybe like anything interesting or like
Yeah,
what
so-
happens when you try to implement these.
Yeah. So, the stuff that, first of all, the things that do best in practice, here we were very kind of rigorous about our hash functions. Even we said, look, we don't want to assume we have a perfectly random hash function. And that made our lives a little bit more complicated. But like things like hyperlog, they just say, you know what, we're just going to assume that our hash function is totally random, even though it's not true, and we're going to analyze it with that assumption, and that's what people use. And kind of the basic idea, it does use a geometric sampling kind of idea. The basic idea of it is, so there again, you can think of it as there are these, a lot of even my data structure with Daniel Kane and David Woodruff also uses the geometric sampling idea. You have this D0, D1 up to D log n. Now, for my data structure with Daniel Kane and David Woodruff, as well as for hyperlog, each one of these Ds is simply a bit vector of length theta 1 over epsilon squared. Let's call this number R. And you're going to have a separate hash function. So let's say this is DJ. You're going to have a hash function GJ, or actually it doesn't need to be GJ. It can just be G. G, which maps the universe into a range of size R. And when you see an item, so now kind of what's the picture? So you just have this these many different bit vectors. So if I just draw it as a matrix, actually there are a lot of columns, right? The number of columns here is R, which is theta 1 over epsilon squared. The number of rows is log n. And you have a hash function H, which maps n into log n. That's the geometric sampling. And you have another hash function G, which maps n into R. So when you see an item in the stream, you first hash that item to a random row, and it's biased toward the higher rows. That's how geometric sampling works. So it's likely to be maybe the first or second row. And then you send it to a uniformly random column, and then you send that, and then you set that bit to 1. So let's say it maps here. So I'll just mark it as I'll mark that box. But basically that bit in the bit vector got set to 1. So, and then, when it's time to query, kind of what do you expect the picture to look like? You expect the picture to look like kind of some prefix of the rows are probably all black. Because if the number of distinct elements is large, then let's say it's much, much bigger than 1 over epsilon squared, then you probably have many more than R items in the top few rows. But then it's going to start to thin out. Then maybe at some point, only a constant fraction, maybe only 2/3 of the row got hit. And then from then on, it starts thinning out geometrically until eventually you have nothing. Okay. And kind of all these algorithms. So kind of my algorithm no, by the way, notice that this would take 1 over epsilon squared log n bits to store. Then you do some more optimizations to really get it down to something much less. They're kind of simple optimizations. So one of them is, you can keep track. So actually, if you want to get the optimal space, here are the optimizations you do. You don't actually
is chop off rows one of them, as soon as they fill up.
So we don't chop off rows. What we do is the following. For each column, we don't keep track of the whole column. We only keep track of the index of the deepest row that got hit in that column. So for example, we would only remember this got hit, 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 this. Just the deepest row in each column. That's a number between 1 and log n. That's only log n bits instead of log n bits. Okay. So now you get a space of 1 over epsilon squared times log n if you ignore the hash functions. And that's exactly the space that hyperlog gets. And then they have some funky estimator based on the harmonic mean. That's what people use in practice. That's it.
Gotcha. Oh,
and then
that's pretty simple.
Yeah, it's pretty simple. And then our data structure says kind of most of these columns, most of these things that you're storing, are pretty close to kind of like some median number. So you can just store, let's say you store the mode. It's not exactly the mode, but let's say the mode. Store the mode of these red numbers as one number. And then for each of these red numbers, what you don't store is the actual number, but you just store the offset from the mode. And the point is, and you store it in like a variable length encoding. So the point is most of these offsets are 0 or close to 0. So they only need a constant number of bits to store. Some of them might be bigger offsets, but that's rare. And then you can that lets you get down to 1 epsilon squared plus log n.
Nice. Thanks for explaining.
Okay, no problem. So I think we're not going to have time for the lower bound. I'll do that next week, Wednesday. Monday is Labor Day, so we're not going to have class on Monday. But Wednesday we're going to do lower bounds, and then we're going to start talking about other interesting things. Distinct elements, of course, is not this is not a class on distinct elements. Okay, so any final questions before your long weekend and having fun?
The lecture notes for this are already up, Professor.
The lecture notes, yes, the lecture notes for geometric sampling are already written with all the calculations there.
Okay, and it also re-describes the algorithm as well, right?
Yep, it's there.
Awesome. Thank you.
Okay. Oh, and I see that there's, let me just look through here. I'll take a look at the chat. Okay, so that was already asked. Stephen suggested. Okay, so it looks like all the questions got taken care of. If not, just ask me on Piazza. I'm happy to answer. Okay, see you all next week.
Thank you. Bye.
Thanks.
Thank you.